Hi there, and welcome to this webinar on pressure vessel testing. My name is Matthew, and this time we're going to have a look at how we can use SolidWorks Simulation to help us analyse and design our pressure vessels. So let's kick off by first of all considering what we mean when we call something a pressure vessel. Now, pressure vessels are used every day all around us, and you can quite easily imagine some big industrial pressure vessel in a factory, like the one you see on your screen now. But how about even larger process pressure vessels like this one? We can also go the other way and make things smaller. Let's, for example, have a look at an oxygen canister used by scuba divers. Even submarines and aircraft are examples of pressure vessels. And essentially what they are is a vessel which is sealed. It has a thin wall in comparison to the rest of the geometry, and it's got some form of pressure inside, be it positive or negative. And all of these designs have to comply with a very strict set of standards or rules or codes, which are set by regulatory bodies all over the world. So for those of you that aren't familiar, pressure vessel codes and standards come in various shapes and sizes. We've got the ASME Boil and Pressure Vessel Code from the Americans. There is a British and European pressure vessel standard. So clearly you can see we have variation with respect to geographic location, but we also have variation based upon application. So here we've got the ASME pressure vessels for human occupancy standard. So this might come into things like decompression chambers. Okay, we've also got an ISO standard for compressed natural gas cylinders, and the American Institute of Aeronautics and Astronautics have their own pressure vessel standard for metallic space systems, so pressure vessels that are going up into space. And this list goes on and on and on, and it's just worth noting, the reason I'm going through this is because it's something that is down to the engineer to know what is relevant. So unfortunately, I'm not going to unleash some revelation that SolidWorks has all of these codes built into it. Far from it. The engineer is the one who has that responsibility of knowing which code is relevant and also which articles within the code are relevant and how they can comply with those. What SolidWorks Simulation is going to do is allow us to conduct stress analyses and gather out the relevant pieces of information for comparison with our pressure vessel codes and standards. Okay, so let's just have a quick look at a typical case scenario. What we've got here on the screen is a pretty typical pressure vessel that I've just put together for the sake of the webinar. So this is what we're going to have a look at in a little while. And it's going to be made of a low alloy carbon steel. It's got a wall thickness of about 2 millimeters. It's about 1.5 meters long, I think. And it's going to be used for the containment and transfer of 700 degrees Fahrenheit steam at an internal pressure of about 165 psi. We've also got, you'll see on the screen, 2 nozzles, one with a lid, one without. And so we're going to assume that there is some form of pipe attached to the open nozzle, and during transit, say for example, the pipe might exert some forces and some moments onto that nozzle flange just there. And so we're going to simulate that as well. It's also worth noting that sometimes you might have to include wind effects and earthquake conditions, etc., etc. We're not doing that here, but it's just a typical sort of scenario that we might have to consider for one of the pressure vessel codes. Now, each of these codes is a pretty substantial document. Each standard can be thousands of pages long. So I've just pulled an extract from one of the ASME codes, and you'll see the address for it just at the top there. But what we've got here is a list of different criteria that must be complied with. So we've got the general primary membrane stress intensity and the local membrane stress intensity. Just while we are there, I'll flip back and illustrate the general primary membrane stress intensity acts in these large open areas where we haven't got any other features, whereas the local membrane stress intensity tends to be around these areas where, say for example, we've got changes in curvature as we reach the dome section, or around the nozzles, or around this reinforcement. Okay, we've also got primary membrane plus primary bending stress intensity, etc., etc. And this isn't a finite list. There might also be other articles that apply depending on the particular design, the materials you've used, and also the specific application of the pressure vessel. So for example, there might be times around humans where the standards are much tighter and the factors of safety have to be much higher, etc. Now, we're all familiar with the term stress, hopefully by now at least, and how stress values can be calculated and analysed for failure. But what you see here is we've got a lot of references to stress intensity. Now, what does that mean to us? Let's have a look. We'll start by considering planar stresses in two principal directions. So here we've got sigma 1 and sigma 2. You'll see on the x-axis we've got our sigma 2 tensile and compressive yield strengths. That's the sigma 2 yield and the negative sigma 2 yield. Likewise, for the y-axis we've got our sigma 1 positive and negative yield points. Now, we should hopefully be familiar from this standard FEA package, perhaps even if you've used Simulation Express. Most of our results default to the von Mises stress. And so we can compare this von Mises stress with the yield strength of our material and determine whether it's yielded or not. And so we can see, if I bring up our von Mises stress limit, we've got this shaded region on the screen which represents the limit based on the von Mises system, and the black line is representing our yield point. So if we have sigma 1 or sigma 2 or a combination of the two exceeding this black line, then we're expecting to see yield. If I bring up our Tresca limit now, this is a yield criterion commonly used for pressure vessels, and you'll see that for the best part of the whole plot, the Tresca yield point is actually lower than the von Mises yield limit. And this is the main reason that it's used for pressure vessels, because it is more conservative than the von Mises stress. The maximum variation we see is about 13%, so sometimes it can be considerably more conservative than the von Mises stress value. So where does this Tresca limit come from? And again, what is this stress intensity? The Tresca criterion states that the shear strength is equal to half the tensile strength. And you'll have to forgive me, but I'm going to bring this up algebraically too. So our Tor yield strength, which is our shear strength, equals sigma yield, which is our tensile strength, divided by 2. You'll also be aware from basic solid mechanics principles, hopefully, that the maximum principal shear stress at a point is equal to half the difference between the two principal tensile stresses, as you can see here. And so when we equate these two, we get this equation. Obviously we can cancel the 2's just there, and so we're left with this P1 minus P3 equals sigma yield. And this term we have on the left hand side, this P1 minus P3, is what we refer to as our stress intensity. So what we're going to do is compare our stress intensity values with our tensile strength to determine whether we're seeing yield. So let's jump over to SolidWorks now and have a look at how that works. What you see we've got here is our study setup. I've got a number of studies which we will come back to, but for the time being let's just assume that my pressure vessel has been set up with a pressure inside, and we're going to have a look at that stress intensity. So I'm going to right click on the results plot and come up to define a new stress plot. And you'll see here, as we're probably used to seeing, we've got the von Mises stress has defaulted into that box. If I drop that down, however, we can select INT, which is our stress intensity, and you can see just there that that is the P1 minus P3 that we did just discuss. For the time being, I'm going to select the membrane. We'll come back to what that means to us in a moment, but I'm just going to hit OK. And so we've got our stress intensity values just there. What you'll notice is our legend is defaulted to the maximum value present, and so we've got 562.4 megapascals of stress just there. If I right click somewhere on one of these models just so I can come into the materials database, we can see that for our alloy steel, our tensile yield strength is about 724 megapascals. So you can see we're well under that limit. So we could say that we haven't reached yield in this material just here. We can also use the two numbers now to determine our factor of safety. Okay, let's jump back into our presentation now and start talking about how we can use the SolidWorks pressure vessel design tool to help us. So SolidWorks Simulation Professional includes a tool called the pressure vessel design tool. And in a pressure vessel design study, you can combine the results of static studies with desired multiplication factors. So each study can have a different set of loads with corresponding results, and these loads can be dead loads, live loads, which obviously we would have to approximate as static, thermal or seismic, etc. We can have almost an unlimited amount of studies with different load types. The pressure vessel design tool then combines the results of those studies algebraically using either a linear combination or the square root of the sum of squares, which can be handy for approximating things like seismic loads. One thing that's definitely worth noting here is that this combination effect doesn't necessarily have to be used for pressure vessels. Any geometry can be used within the pressure vessel design study, and so we can combine different loading conditions for any geometry, so it doesn't specifically tie us down to designing pressure vessels. So for those of you that perhaps may have overlooked it, you can set up studies for any design and combine those linearly or using the square root of the sum of squares to analyze your model, including multiple studies. Also, what the pressure vessel design tool allows us to do is linearize our stress results through the wall's thickness of solid meshed components. So you'll see in a moment that we've used shell meshes for the majority of our model. Now, that's easy to gather our membrane and bending stress components. We will come back to this in a moment, but it's not so easy with solid meshes. SolidWorks Simulation Professional has the capability to linearize these results. So we've got a tool available to us to linearize the stresses through that wall thickness and extract those membrane and bending stress components, which are important because they are normally the key criteria used in the pressure vessel standards and codes. A couple of important notes before we do continue. When you are using the pressure vessel design tool, you can only vary the loads. So our fixtures, our contact conditions, our materials, our geometry must all remain the same. It is only our loads that are varying. The results must also be in the linear range, so we can't use the large displacement option, and we can't use no penetration contacts. There is one caveat to that. We can do that if they are already in contact. The reason we say we can't use them is because we can't have components coming into contact during the course of the study and generating contact stresses as a result there, because that presents a non-linearity in the stress condition. And finally, it's kind of a common sense one, this one, but for the square root of the sum of squares combination, we can't use displacement or deformation plots, because when we take the square of a negative number, we remove that negative sign. So our negative displacements will suddenly become positive, so we'll get largely inaccurate displacement and deformation plots. Okay, so just as we're about to jump into SolidWorks and have a look at the pressure vessel design tool, let's consider the first bullet point that we saw in that extract from the ASME code, and that's for the general primary membrane stress intensity. And we're going to assume that our membrane stress intensity limit is about 38 KSI, so our membrane stress has to be less than that. There's a brief explanation on your screen just here of a definition, if you will, of the general primary membrane stress intensity. I'm not going to go into that too much. You could pause it and have a read through it, but essentially it's just saying that this criteria is used for the large areas where we haven't got any other features, and also so that no redistribution of loads occurs as a result of any yielding in any of these areas. Okay, so let's have a look at our study now. And what we've got, first of all, is our pressure study. So this was the one we just had a look at. And first of all, you'll notice that in the list of components, I've got a lot of shell meshes, and these have been defined afterwards. So if I just come in and use the section tool to have a look inside our model, you'll see we have got thickness in all of our components. So they haven't directly come through as shell meshes. Instead, what I've done is defined them as shell meshes by selecting the external face like this. So you'll see here I've selected an external face just there, and that comes important when we come to applying our loads. So you'll see for our loads section we've got pressure applied to the external face of that pressure vessel, and that is because we have selected that external face to represent our shell mesh. So we have to make sure that the face that we're applying the load to is the same face that we used to define our surface mesh, and that's why these arrows are on the outside pointing outwards. It's worth noting that you do still need to make sure that they are pointing in the right direction. You'll see we have got three solid components at the bottom here, and these are our nozzle flanges and the nozzle cover just there. And we've used those because they've got geometry that lends itself more to the solid elements than the shell elements, and we'll come back to that in a moment. We've got some bolts that we've used here to fix the cover onto the nozzle, and we've also got a number of contacts set up. I won't go into that too much. Setting up your study is a pretty basic thing that we've covered in other webinars. I put some mesh controls onto the manhole covers and flanges, and also the contact point between the supports and the pressure vessel, and also I've got a fixture on the bottom of the feet just there. Okay, thermal study. I've just applied a global temperature to all of the external faces. The self-weight study, I've just applied gravity, and the inlet nozzle force, I've just applied a force and two moment forces to the nozzle flange, just where you can see my cursor moving around now. Okay, so now let's jump into our pressure vessel design tool. So you see at the bottom of my list here we've got pressure vessel design. I'm just going to change this name. We'll call this pressure vessel. And so you'll see we've got a much more trimmed down simulation tree. There isn't much to it. All we need to do is right click on setup and select define/edit, and you can see up the top here we can specify whether we want a linear combination or whether we want to use that square root of the sum of squares. And in this box here all we need to do is select each of our studies. You'll notice I'm not including the thermal study. This is because I've had a read through the standard, and for this particular criteria, the general membrane stress intensity, the thermal study isn't necessary. We don't include thermal effects for that criteria. You'll also see here that I can click in any of these boxes and change the multiplication factor to, for example, 2. So now we have twice the pressure study being included. I'm going to put that back down to 1. And I just need to hit OK. Now, the rest of the study runs pretty much the same as a standard simulation, so I can right click here or I can select run at the top, and it's just going to do all the calculation for us. Now, luckily, each of these studies took about 2 hours to solve, but the pressure vessel design study simply uses results that have already been obtained algebraically. So you'll see that that solve is very quick. And if I expand the results folder, we've got displacement, stress and strain results as we would usually see, and this is where the use comes in for combining other studies. So when we said that we don't necessarily have to use pressure vessels in this tool, this is where we can reap the benefits, because it's exactly the same environment as we had with the standard studies. We've got all of the usual tools available to us. Okay, next let's just have a look at our stress intensity. So I'm going to come back up here, grab that stress intensity. This time I'm going to use KSI because we're going to compare it with our standard value, and we're going to select the membrane stress. And so you'll see here our peak membrane stress has come in at 82.3 KSI, and that seems to be in a couple of localized regions. Now, one thing that we did say when we were talking about our standard criteria was that it was in the large open areas of the pressure vessel itself. So what we're going to do for the time being is hide that plot and just isolate the pressure vessel itself. Now I'm going to replot that result and then come into the chart options and ask SolidWorks to plot only the minimum and maximum range for the shown parts. And what that's going to do when I replot this now is update the values on the legend so that we can see the maximum values present. So you can see here the maximum value is dropped down to 51.4 KSI, but it is localized around these nozzles, around where that reinforcement bar is, and also this change of curvature where we're reaching that dome section. So we might say, well, that doesn't actually fall into the general primary membrane stress criteria. So we're only concerned in these values. So let's change the chart options. And instead I'm going to create my own defined set of axes and make this 38 because that's the limit for our general membrane stress. And now everything that's red is exceeding or equaling that limit, but you'll notice that still in all of the regions that actually fall under the general primary membrane stress intensity criteria, we're still not reaching that limit. So we could say that our design is safe in this case. Okay, let's just jump out of there now. I'm going to hide that. And now our nozzle flanges and the cover have been analysed, like we said, using solid elements due to their thickness against span ratios, and also because we have included the bolt connections on the lid side. Now the ASME codes don't specify the limiting stress intensity values for these components. Instead, for flanges, it states limiting values of longitudinal, radial and tangential stresses. So let's have a look how we can define plots that help us analyze that. First of all, I'm just going to bring up an axis so we can see that just there. That will come into play in a moment. And I'm just going to isolate the flange, so we're just going to analyze this flange here for the time being. You see that axis is a center point axis for this flange. And I'm going to right click on the results folder, define a new stress plot. And this time, instead of using either the von Mises stress or the stress intensity, I'm going to use these normal stress values. So we've got Sx, Sy, and Sz. If, for example, I grab that Sx value, we get a reference set box appear. And what that allows us to do is grab that axis and use that as our reference coordinate system. Now, because we've used an axis, when I hit OK, you'll see we get this plot just here in the bottom right corner, which shows us we're using a cylindrical coordinate system. So now instead of our XYZ components representing the XYZ directions of our global coordinate system, instead we've got our X, Y and Z have been transformed such that X now represents radial stresses, so stresses acting from the center outwards. Our Y represents tangential or circumferential stresses, so these are stresses about the circumference, and then our Z component represents axial stresses, so these are stresses acting in the axial direction. And so using this plot we can gather what the maximum radial, tangential and axial stresses are in our flanges, and then we can draw those comparisons again with our pressure vessel standards and codes. Okay, let's just hide that. And finally, the ASME code doesn't specify that we need membrane and bending stress components for the flanges and covers, but we may encounter a time when there are other bulky components that will require these values. So for example, our reinforcement sections here around the nozzles might be done using solid components. We might need to calculate the bending and membrane stresses for those. Perhaps in the standards, the criteria for those are with respect to bending and membrane stresses. So what we're going to do is come in and use what's called the linearization tool to gather that sort of information from our solid mesh components. So I'm just going to hide this axis again. And because we haven't got any other thick geometry, I am going to do this on a flange. So let's first of all isolate this flange again. And this time I'm going to plot the stress intensity. And then I'm going to use the section clipping tool and I'm going to switch that to the right plane. And what this is going to allow us to do is see the cross section of the material. So this is important because this is where we are going to linearize across. So if I'm just going to hide the section plane and select that. We want to linearize the stress information from one side to the other through the thickness of this flange. So if I right click on the intensity plot now, you'll see we have got another guy that's joined the list, which is the linearize tool. If I select that, we get the prompt to add some points or locations to the plot. So I'm just going to grab one on the front and one on the back, and ask SolidWorks to calculate. You'll see here we do also have the option to change the number of intermediate points. So what SolidWorks is going to do is stick a number of points in a line in between the 2 points that we've selected, and it's also going to use those for its linearization process. And now you'll see we've got our 2 points that we've selected highlighted with these captions on the screen, point 1 and point 2. And we've got the line representing our linearization location. If we expand this box, we can see our results. So we've got membrane stresses, and we've got our bending stresses come through here. We've also got the opportunity to plot these. So if I click the plot button, we get outputs in graphical form of all of our stress components. So we've got our normal X, our normal Y, our normal Z, and we've got our shear in XZ, our shear in YZ, and our shear in XY. So these are our linearized stress components. Okay, that might be something that's probably more useful and more clear to those of us that have used linearization tools before, or those of us that have had to perhaps do it by hand. It's quite a niche thing that's mainly used for pressure vessels. You've also got the opportunity to save this information out. So I'm just going to click save and place this on my desktop. And what this lets us do is save out the comma separated variables files with all of the information that SolidWorks has used in that linearization process, as well as the outcome just at the bottom there. Okay, that is about all I've got time for. That's a pretty good summary of the pressure vessel design study tool. If you have any questions, please don't hesitate to get in touch. You can do so by dropping by our website, which is innova-systems.co.uk. You can send us an email, which is at support@innova-systems.co.uk, or you can call us on the number you see on your screen now. Don't forget also to join us for any future webinars. Next, we've got on the 21st of June, beam analysis with Alex.